Light-independent reactions are going to happen inside of the chloroplast in the empty space. We don't really say empty space, but inside of the goo within the chloroplast and the stroma. This is outside of the thylakoid membrane. And we've got a series of enzymes that are going to go through multiple metabolic steps that, like we talked about with the citric acid cycle, is going to go cyclically. Light-independent reactions are also sometimes called the Calvin cycle because the name of the guy who discovered it, his last name was Calvin. Or they're also sometimes called the dark reactions because we're not going to use light energy or photons to go through this whole process. However, it does depend on light from the light reactions in order to allow for the things we're going to list right now. So let's talk about what the reactions are, and then we'll come back and describe some kind of things to remember when you're going through these. So we're gonna you could start anywhere. It's a circle. I usually start over here with a molecule that is called ribulose bisphosphate, and ribulose bisphosphate has got 5 carbons inside of it, and then on either side of the 5 carbons are phosphate groups. And so we got 5 carbons in the middle, and then a phosphate group and a phosphate group. And those 2 phosphate groups are why this is called ribulose bisphosphate. Bis for 2, and then bisphosphate, we have 2 phosphate groups. The sugar in the middle is just ribulose. So ribulose bisphosphate is going to bind to a single molecule of carbon dioxide. And the enzyme that is going to do that is called Rubisco, and Rubisco is going to smush CO2 onto RuBP, and it's going to let us produce, when we put the two together, this really short-lived 6-carbon intermediate. And so the 6-carbon intermediate is basically going to be the 1, 2, 3, 4, 5, and our phosphate group. Our 5 carbons are 2 phosphate groups, and then this new carbon is going to bind to carbon number 2. There's our CO2. We get this 6-carbon intermediate. It doesn't usually even list a name inside of most of the textbooks, and that's because it only exists for a really small amount of time. It's very unstable. And it's going to snap apart, and it's going to snap like right here. And when it does that, we're going to get 2 3-carbon sugars. And so we've got 3 carbons and then a phosphate group over there, and we've got 2 of these. And this molecule that we make is called 3-PGA, which is 3-phosphoglycerate, is what's going to be produced. So 3-phosphoglycerate or 3-PGA, and we got 2 of those, and we know we have 2 because each only have 3 carbons, and our intermediate had 6. So 6 divided by 2 is 3. This sugar is really no different from our RuBP in terms of like its nature of carbons and bonds and things like that. The difference is that this molecule incorporated this CO2 that used to be in an inorganic form. We'll talk about that more in a second. So now our 3-PGA, we want to juice it up. We want to make it this high energy version of this carbohydrate. And so the first thing we're going to do is make it unstable by adding more phosphate groups. And so we're going to use up ATP. We use up ATP to attach phosphate onto the 3-PGA. So now we got 1, 2, 3 carbons, phosphate, phosphate on both sides. Okay, so this molecule is the same as that one. The difference is now we have 2 phosphate groups instead of 1. This one, because it now has these 2 phosphate groups, is called 1,3-bisphoglycerate. Okay, and now this guy, we're going to juice up even more by now adding high energy electrons. So we're adding high energy electrons from NADPH. We've seen NADH during the citric acid cycle and the electron transport chain of respiration. In plants, for photosynthesis, it's NADPH, but it has the same purpose in that this is carrying electrons. So it's going to come over, it's going to drop off its electrons and just go back to being NADPH positively charged. And we've still got our hydrogen ions over here. So we got our NADPH, it dropped off its electrons, and so now those electrons are inside of this molecule of 1,3-bisphosphoglycerate. Also, when we do that, we're going to lose the phosphate group. So 1 phosphate group is going to come off, and we're going to be left with this sugar that has got 1, 2, 3 carbons and a phosphate group. Okay, and we're actually going to have two of them. I'm only drawing one at a time just so our drawing doesn't get too confusing. But remember that this is going to happen twice because we had two 3-PGA, which came from this one molecule of this 6-carbon intermediate. This sugar that we've just made down here that has 3 carbons is called G3P. Okay, and again, we've got two of these guys. All right, you might look at the drawing and say, well, why does this have a different name from that one? And why did we do all these steps to produce this sugar that structurally looks exactly the same as this one, the 3-PGA? So 3-PGA has got 3 carbons in a phosphate group. G3P has got 3 carbons in a phosphate group. The difference between these two is that G3P is a higher energy form because it contains the electrons that were on this molecule of NADPH. 3-PGA is formed before we use up the NADPH, and so it doesn't have those high energy electrons. And so although they're both sugars, although they have the same number of carbons and they both have a phosphate group, G3P is a higher energy version of this 3-carbon sugar. It is easy to confuse them because they have really similar names. For whatever reason, I just try to remember that the one with the number 3 at the beginning is the first one, and then the one that doesn't have the number at the beginning comes second. So that's G3P. Okay, so G3P is kind of like our product. That's our higher energy sugar. We could take this and go off and do work with it because it has these high energy electrons, which is what we use during cellular respiration. The problem is that if we took both of those sugars away to go do something else, we would have nothing left to get us back to the beginning again. And remember that this is a cycle, and so we don't want to use up all of our stuff. So what's going to happen is one of these is going to leave. We're going to take one molecule of G3P away, and we could do all sorts of things with it. We could turn it in, we can go through multiple subsequent steps, and it could find another G3P, and we could get glucose. It's a 6-carbon molecule, so we smush 2 of these together, and we get glucose. It could also be converted into pyruvate, which has 3 carbons, and it could enter the citric acid cycle as pyruvate or after pyruvate oxidation. We could also clip one of those carbons off, and we get the 2-carbon version, which is acetyl. So there's all sorts of things we could do with this G3P so that we can produce ATP from it with any of the steps along normal aerobic cellular respiration. So that's like our product. We're going to take that. That's our pay. But the other G3P we're going to keep inside of this whole system, and we're going to use it to get back to this molecule of RuBP. So here's our molecule of G3P, and we want to be able to get from G3P back to RuBP. And we don't want to use any new molecules, we don't want to bring anything into the equation, and we also don't want to have any leftovers. So in other words, we need to recombine or use molecules of G3P to remake RuBP. So you can say, okay, well, why don't I just get some more CO2 and add them onto the G3P twice, so that I add 1 carbon and 1 carbon and get RuBP. And it doesn't work like that because Rubisco can only make this guy. It can only work with RuBP. That's a whole thing, adding the CO2 on. And so we can't just simply add carbons onto there. You'd say, okay, well then I'll get 2 G3P, that'll give me 6 carbons, and then I'll just take one of the carbons away, and then I'll get RuBP. And then you'd end up with 1 carbon all by itself. You'd have this leftover orphan carbon, and we can't do that. We want to get from here to here without any leftovers. And so we just keep going up the line. You can imagine, okay, well if I had 2 G3P, it doesn't work because I have 1 leftover carbon. If I've got 3 G3P, now that's 9 carbons, and that'll let me make 1, but now I got 4 leftover carbons. Just got to keep going on until we find out with an even number of groups of 5. And so what's going to happen is this is going to go through multiple steps, and eventually if you're doing like a more higher level biochemistry class, you might go through all of those steps. For our purposes, just this general bio level, we're just going to put a bunch of arrows to indicate things are going to happen. And what's going to happen is we're going to put ATP into this system, and we're going to basically get 5 G3P. And you can imagine that if we had 5 G3P, that would be 15 total carbons. Because they each have 3 carbons, we got 5 of them, that's 15 total carbons. And if we had this huge long molecule that's 15 carbons long, we could break it into 3 equal pieces that all have 5 carbons. And that's like our RuBP. And so we're going to get a whole bunch of G3P together. We're going to make this really long chain of a 15 carbon molecule. we're then going to break it into 3 equally sized chunks that all have 5 carbons and add 1 more phosphate from an ATP, and that's how we're going to get back to RuBP. And so your textbook will indicate that in a number of different ways. If you're looking at your textbook, you might see through each of these steps that they've got little numbers to the side, like maybe it says 3 carbon dioxide instead of just 1. Maybe over here it says like 6 3-PGA instead of just 2. And it just depends on the way that they're doing their math, how you're accounting for what's going to happen. I just try to do it in the most simplistic way, which is 1 CO2 with 1 RuBP. But essentially we're going to recombine those numbers over here to regenerate that RuBP. So each section of this whole thing has got a different name for it, because we've got multiple steps. We've really abbreviated them in the drawing that we made, and so we can kind of group them up into 3 stages. The first stage is from here to here, which begins with RuBP, adds our CO2, and then creates or ends with our molecules of 3-PGA. And these stages are called fixation. And that is because this step in particular, where you add CO2 onto RuBP and get this 6-carbon intermediate, that is done with the enzyme Rubisco. And that is a super ultra important enzyme. Rubisco is the only enzyme on the planet that is able to take a non-living inorganic version of a molecule of CO2 and cause it to become a part of this organic sugar. It's the equivalent of you just like picking up a rock outside, squeezing it, and then it just turns into like a dragonfly or a squirrel or a mouse or something. It's like Rubisco is making life out of not life when it takes in that CO2 and makes it a part of this organic molecule. This is a really important step, and that's basically the origin of the ecosystem on Earth, is what Rubisco is able to do. And so this step is called fixation. We are fixing the carbon and turning it into an organic reactive form. The next series of steps from here to here, we're using up our ATP, we're using up our NADPH that we created in light reactions, so that we end with G3P, which is our high energy energetic sugar. And so this series of steps is called reduction, because we are reducing our molecule of 3-PGA to become G3P. Remember that in redox reactions, reduced forms are the high energy forms. They're the ones that contain the electrons. And right here, this is the step where we're dropping those high energy electrons off so that they become incorporated into this molecule of G3P. So we got fixation stages, which lead to the reductive stages. After reduction, we've gotten our payday. We took our G3P. And so now we're just involved trying to get back to RuBP. And so these steps that begin with G3P and end with RuBP, these are called regeneration. Because during regeneration, we're just trying to regenerate the RuBP that we began with so that we can do the cycle all over again. So we got fixation, reduction, regeneration. Notice that in most of the time you're talking about metabolism, you're talking about, making ATP. When you're talking about cellular respiration, you're talking about how many ATP can you get, what can you do with these molecules to produce ATP, because the goal is to make ATP. During the light-dependent reactions, so not these, but the light-dependent reactions, we also are making energy. Here, notice we're using energy. We're using up ATP. We're using up ATP. We're using up NADPH. We're not making it. This whole series of steps consumes energy. This whole thing is going to cost the organism energy. But the reason why it is still beneficial to do is because it is the light-independent reactions. The ATP and the NADPH that we're using up is the same ATP and NADPH that we generate during the light-dependent reactions. So the chloroplast is going to make ATP and NADPH and then send it out to the stroma, and then in the stroma we're going to use that energy to create this sugar. And the ATP that we're eventually going to get from the G3P, from the sugar, is greater than the energy that we consumed to make it. So overall, this is still a favorable process. We're still coming out ahead in the end. We're going to be getting more ATP than we're investing. But this is the step that is consuming energy in order to produce this sugar, which contains the high energy electrons that came from NADPH, that came from the light-dependent reactions within the thylakoid of the chloroplast.